talk about the query optimization. So we have added in the past year for our workload in Meta. So yeah, let's start now. So I'm going to first give some overview of the optimization we have added, and then I'm going to talk 3 optimizations in detail. So for the optimization we have added, we focus on the query rewrite optimization. So this is because this optimization can benefit both Presto Java and Prestissimo. And also all these query rewrites, they come from the production workload we have seen in our within Meta. So the first one I'm going to talk about is join prefilter we added this year. So for the join prefilter, what it doing is it filter the right side of the join with the unique values on the left side. So this is the equivalent SQL rewrite for this organization. So instead of join the left table and the right table on the join key, so we're going to first do some prefilter on the right side. So we're going to filter the join, the rows on the right side with the key on the left side. And then we're going to do the join. And this is how the query plan looks like before the optimization and after the optimization. So the question is what kind of workload can benefit from this optimization? So there are 2 requirements. The first one is for the join, it should have low selectivity. That means most join keys on the right side will have no match on the left side. So that after the prefilter, we're going to have a much smaller build side for the join. And the second one is that the left side have large payload. For example, feature maps, which is quite common in machine learning workload. And also it has only a few unique join keys. So that the semi-join will be very cheap, because this is additional cost introduced by this optimization. Now let me give you a very simple example of how it works. So on the left side, these are the tables for the join. So we have the table L and the table R. For table R, we have 4 rows. And after the prefilter, we're going to have only 1 single row for table R. So this is how we reduce the size of the build for the join. And this is a performance improvement we observe in one of our machine learning workload after applying this optimization. So the horizontal axis is the time which when we apply the optimization. And the vertical axis is normalized latency. So we see great improvement for the latency after we apply this optimization. So because this optimization is so useful and our user love it so much, so we do further improvement for this optimization. So the first one we did is that we found sometimes the join key can be large. For example, if the join key is a string, the semi-join sometimes can wound. So what we did is we, instead of a prefilter on the join key itself, we build a hash from the join key, and we prefilter on this hash itself. This hash is long integer. And the second improvement we did is that we target, so for join with multiple join keys, it's not easy to use a semi-join for these multiple join keys. So what we did is for each join key, we're going to hash the join key, and we're going to combine this hash into 1 single hash. Then we use this single hash to do the prefilter. So these 2 improvements have already been implemented. And we also have a plan to add this to history-based optimizer in the future. So this is for the join prefilter. The second one, I want to talk about the sharded join. So the sharded join is to mitigate skew for join. So it targets workload which has data skew. However, the build side is not small enough for broadcast join. So this is example for the query, equivalent query rewrite for this organization. So instead of like join left and right directly, on the left side, we are going to attach one random number between 0 to n-1, which we'll call it a shard. And this is where the sharded join name comes from. So on the right side, we're going to first attach a sequence from like 0 to n-1. Then we unnest on this sequence as a shard. So basically here we are replicating the build side, the right side, by n times, where the n can be specified by us. And now we are going to join on both the join key and the shard. Now let me show like, yeah, this is the query plan before and after the organization. So let me show you an example of how this works. So this is a simple example where we have like two tables to join. So for the left table, it has skew, where like we have many ones in the join table. It means that like most of the workload is going to go to worker 1 during the join. So with this organization, so like we are going to, on the left side, we are going to first like add a shard to this like left table. And for the right side, we are going to like add a sequence from 0 to 1, then unnest it, and then since now we are joined like by both join key and shard, the workload is distributed more evenly compared to the previous example. So basically you can think about this. So let's say like we have like a cluster with like 1,000 nodes. So for broadcast join, it's like replicate this like build side by 1,000 times, which like can be not be like doable for like some table which is not like small enough. And for this sharded join, we're like replicated by n times, where n can be small, so like 10 or 20 or 100. So yeah, so this is the sharded join. And the last one I'm going to talk about the map cast removal. So this is also one pattern we observe in our workload. So sometimes for the feature map, the map can have like integer as the map key. However, like sometimes people use like a big int to access the map. So currently the code will upcast the map from map int float to big int float, which can be expensive at some time. So we rewrite this path so that we are going to like cast the key instead of the map. So this is like a performance improvement after we apply this optimization to one of our workload. So the cost say like about a 100 time improvement after this like optimization. So yeah, these are three optimizations I talked about today. And I want to acknowledge Srini and Lulana who also contributed to these optimizations. And all these optimizations are available in open source. These are the link to the three optimizations. And thanks. Yeah.